Throughout our incredibly vast universe, billions of trillions of stars are creating the elements that we interact with every day, as well as others we don't even know exist yet. They do this through nuclear fusion, the process of fusing two separate atomic nuclei together, creating larger nuclei containing a greater number of protons, a different element entirely. An atomic nucleus contains two things, protons with a positive charge and neutrons with a neutral charge, giving the nucleus an overall positive charge. These subatomic particles are held together within the nucleus due to a force known as the strong force, one of only four known fundamental forces of nature. Nuclei repel one another as like charges repel due to strong electrostatic repulsion, making fusion difficult. Nuclear fusion occurs when the two nuclei become close enough that the strong force overpowers the electrostatic force, pulling the nuclei together. At distances of around 1 femtometer, the strong force overcomes the electrostatic repulsion. To get the nuclei close to one another, a system requires an extremely high temperature, an extremely high pressure, or a combination of the two. In our Sun, its enormous mass means that its gravitational field creates extreme density in its core, pushing nuclei close enough together to fuse. As electrostatic repulsion increases with charge, our Sun doesn't have enough pressure or temperature to fuse larger nuclei than hydrogen. However, other larger stars have, or historically have had, enough mass to create the elements that we know today. The Sun mostly fuses two hydrogen isotopes together, deuterium and tritium, which fuse to create helium as well as a lone neutron. When the masses of the reactants and products in a fusion reaction are compared, it is consistently found that there is a loss of mass during the reaction. This mass is converted into energy, which can be found using Einstein's most famous, beautiful equation E equals mc squared, where E equals energy, m is mass lost, and c equals a constant, the speed of light. Each individual reaction only creates a small amount of energy, however that is for one single nuclei, thus enormous amounts of energy can be produced. For example, one DT reaction has a mass loss of 0.0188 atomic mass units, or 3 times 10 to the minus 29 kilograms. This outputs 2.7 times 10 to the minus 12 electron volts of energy, a tiny amount. However, when multiplied by the amount of fuel in a regular glass, this makes 9.6 times 10 to the 34 electron volts of energy, or 4 times 10 to the 9 kilowatt hours, enough to power 400,000 houses for a day. You would have to burn almost 4 million barrels of coal to get that much energy. Research into nuclear fusion as a power source began in the 1920s, when the sun's energy production method was first discovered. Fusion on Earth has the potential to be much more sustainable than any current energy production method, and could provide the solution to the current energy crisis. On Earth, we don't have access to a ginormous mass with extreme gravity to create a high pressure for us. Instead, we have two main approaches to achieving fusion on Earth. The first, inertial confinement, uses powerful lasers to both heat and compress a pellet of fuel, achieving fusion. The second, the Tokamak, uses electromagnets to confine a plasma into a specific region, achieving fusion. For all of these reactions, the best fuel is the same as that in the Sun, deuterium and tritium. We have plenty of deuterium on Earth, however tritium is much harder to find as it only has a half-life of 13 years. It is possible, however, to utilize the neutron produced in the fusion reaction to react with lithium-6 to produce tritium, making lithium and deuterium the primary fuels. To achieve self-sustained fusion reactions in a tokamak, a high temperature greater than 100 million degrees Celsius, high-density deuterium-tritium plasma must be stably confined with a confinement time greater than 1 second. The tokamak fuel is heated externally by first accelerating positive hydrogen ions to a kinetic energy of 1 mega-electron-volt using electric fields. The hydrogen ions are then neutralized before being injected into the fuel. This heats the fuel up to around 150 million Kelvin, 10 times hotter than the center of the sun. At this temperature, the fuel exists as a plasma. Plasma is the fourth state of matter, consisting of a gas of ions and free electrons with extreme kinetic energy that move randomly due to their thermal motion. The existence of fuel in this ionized form allows for it to be manipulated in a few ways. Such high temperatures preclude confinement by material walls, and thus another method of confinement is required. The ionized plasma has the ability to conduct a charge, allowing it to also respond to magnetic fields. In the tokamak, a plasma is confined to toroidal field lines created by the tokamak's toroidal current carrying coils. This field alone does not allow confinement of the plasma, however, and a poloidal field is created to confine the plasma vertically. The combination of these fields creates magnetic field lines in a helical shape around the torus. The toroidal and poloidal coils are made of superconductors that carry a current, producing the magnetic fields. A change in flux due to a third coil at the center of the tokamak induces a toroidal electric field, driving a toroidal current through the plasma. Changing the current difference between poloidal and toroidal coils allows for the plasma to be confined to different shapes, optimizing fusion. At a high temperature, toroidal current conduction decreases, and an equilibrium between temperature and conductivity needs to be achieved. Optimally, the fusion reaction should produce enough energy to sustain fusion reactions, as well as absorbing heat energy into a blanket, which then transfers the heat into an external heat system, which utilizes a turbine to produce electricity. The primary expense in creating fusion is the energy required to heat the fuel, which at present is much larger than the energy actually produced. The superconductors are only effective to sustain a magnetic field up to around 16 teslas. This limits the toroidal current achievable, in turn limiting confinement time. The other factor that affects confinement time, however, is toroidal radius, and thus, larger tokamaks are being built to create longer, therefore more economical fusion. Taking into account the maximum current achievable, the relationship between toroidal radius and confinement time has been found at about a half radius squared seconds. Successful fusion has already been achieved. Alchemy and bigger tokamaks are being created, along with advancements that will hopefully make fusion one day financially viable, giving us almost unlimited access to sustainable energy. We might even be able to use the helium byproduct to make zeppelins a part of our future.